right, let's do a simple example here. So here's the relationship we're going to use. Let's consider the following. Let's have elements that have two nodes on an edge. And again, this could be either edge of constant strain triangles or Q4 elements. And we're going to have a traction that's uniform in the normal direction. So I'm going to give this value P. It's going to be constant. That's going to be really the T of X, right? It's constant, okay? All right. So if that's the case, let's substitute this state into this equation and see what we get. Well, if we look at, well, let's just pick this element. This has a length here. So let's put in the shape functions, right? So if we have an element here, it's going from S1, S equal 0 to S equal 1, all right? I can write the shape functions on this edge. The interpolation with respect to S, is just going to be N1 is equal to 1 minus S. This is if S is 0, we get a value of 1. If S is 1, it goes to 0. And then N2 of S is going to just simply be S. All right? So if we were to look at the shape functions, you can see on this edge, right? N1 goes up to a value of 1 and then linearly drops down to 0. And N2 starts at 0 and goes up with a constant slope up to 1. All right, so those are the shape functions on that edge. We just really need to integrate on that edge. Okay, so writing this, we now get so we're going to integrate from 0 to 1. The shape functions are just 1 minus S. The traction is a constant. It's got a value of P. It's got an edge length of LE. And then we're going to just integrate with DS. These guys are constant. They come out. And then now when I take the integral of this, I get an S minus 1/2 S squared, and then a 1/2 S squared, and we're going to evaluate this at 0 and 1. The 0 ones all go to 0, so this just leaves me with P, length of the element. 1 goes into here, that gives me a 1/2, and then 1 goes into here, and that also gives me a 1/2. Okay? So this is what you would expect. If you look at this, what are we getting? Well, P times the length of the element, right? That's the net force on this edge, right? P times the length of the element. That's the total force acting on this edge. And what it's saying is you put half at one node and half at the other node, okay? So for example, if P is equal to 50 pounds per inch, and here's an element whose width here is let's call it a 0.2 inches, all right? Then what that would mean is the total force acting on this edge would be the 50 times 0.2 inches, or that is 10 pounds, right? And you would actually end up having to put half at this node and half at this node. So you would have 5 pounds here and 5 pounds here, okay? Now, that's the contribution from one element. So if we had that situation, let's look at an edge with 3 elements. Let's make life a little easier. Let's assume all these have a distance of 0.2 inches. All right. And again, we're going to assume that we have a constant distribution on this edge of P equal to 50 pounds per inch. All right. So if we look at this node, right, let's consider the first element. This element would contribute 5 pounds to this node, and then 5 pounds to this node. Same as that calculation. All right, then we move to the next element. This would contribute another 5 pounds to this node, and then 5 pounds to this node. So actually, at this node, the actual force you're applying here is the sum of these two, so it's 10 pounds. And likewise on this node, we put the another 5 pounds here from this element, and then the 5 pounds on this edge. Now, since these two outer nodes don't have any other elements next to it, they're going to stay at 5 pounds. So the actual distribution we're going to have, the correct one, is as follows. Well, 5 pounds here, 10 pounds here, 10 pounds here, and then 5 pounds here. So that's actually what you should put on that edge. And again, this is whether there's constant strain triangles or quad force. That's what you would put on the edge. Now note the total force here is 30 pounds. This distance here is 0.6 inches. And so 0.6 times 50, the total force acting on this whole edge is also 30 pounds. So these numbers match as you would expect that they would, all right? So what you don't want to do, what would be incorrect, is to say, okay, we have a total of 30 pounds on this edge. I'm going to divide that evenly up between the 4 nodes. So that would be, well, 30 divided by 4 would be 7.5 on each, right? 7.5 pounds, 7.5 pounds, 7.5 pounds, 7.5 pounds, right? Still adds up to 30, and they're all equal. That is incorrect, all right? What that is effectively doing is it's not uniformly distributed. What that's modeling is uniformly distributed here, the higher load, and then a little uptick at the end, okay? Okay, and so that's incorrect, all right? It should have this. So the easy way to just do it, when you have the 2 nodes elements, you know, figure out, the way I tend to think of it, and you know, this might be useful for some people, you kind of look at this and you say, well, okay, this node kind of has support on this edge, and this has a length of 0.2. So you get a contribution of the 10 pounds times the 0.2 goes completely on here. So that, I'm sorry, 50 pounds per inch over the support area of 0.2 inches, that gives me 10 pounds. Now this side node has a support area of like 0.1 inches. So 0.1 times the 50 pound inches gives me 5 pounds. Okay, that's actually not technically correct, and I'll show that in the next video when we have higher order elements. But for elements where you have linear interpolations on the edge, like this one, constant strain triangles or quad 4s, that's appropriate. Okay.